Chapter 12 is all about solids and modern materials. Now, this chapter does go really deep into something called unit cells and lots of different types of solids, but we're really just going to focus on the basics and we'll just touch on some modern materials at the end since they're pretty cool. So, jumping in, let's just think about really quick how we have what materials are made out of. So, we talked about this earlier in chapter 11, but we have if I just have metal, then we know that that would just be metallic bonding that is happening. If I have just, if I have a metal and a nonmetal, we know that it is ionic. And then there are a couple things that are going to be different here. So we've seen metal or just nonmetals bonded together. And we know that is a covalent bond, but there are going to be two different types that we'll talk about. So let's give some examples for this. So metallic, like let's think about a solid, that's a metal. Let's just talk about copper. So copper, it just as a solid, it's a bunch of solid copper atoms held together by metallic bonding. So we'd call that a metallic solid. If I have a metal and a nonmetal, that's ionic. So let's think about like sodium chloride, right? A metal and a nonmetal solid, and that's an ionic solid. For the two different other types, we have big, long structures like, let's say, like quartz. Quartz is silicon dioxide, but it's not an individual unit. It actually looks a lot like an ionic compound where it alternates in space, held by lots and lots and lots of covalent bonds. That's different than something like carbon dioxide, where carbon dioxide, it is held together, right, by two covalent double bonds, but it's not extending into other bonds, right? This carbon is not going to bond to another oxygen from another molecule. This whole molecule, this individual unit, if it's a solid, it's going to be held together by IMFs. So we have this first one with silicon dioxide, like glass, where it's more like a lattice structure. That's called the covalent network. Because, again, it's like a lattice, like a network, but all held together by covalent bonds. And then we have carbon dioxide, which is held together by IMFs. And so if you're held together by IMFs, that's called a molecular solid because it's an individual molecule. Versus silicon dioxide, it's not an individual molecule, it's actually a huge network. So back to the notes. So again, metallic solids are held together by metallic bonds. We kind of think of this as our protons in the middle, right? Our nucleus. Let me write those out. We have our nucleus in the middle, and those are thought of as stationary. And then we have our valence electrons that are able to kind of float around between between the different atoms, and like that's what causes conductivity, because it's more of like a communal electrons that are shared and they're easily able to flow. So if one electron gets knocked over to this atom, then another atom next to it might have some knocking into it, and that causes the electrons to be able to conduct. We also have ionic solids, which are cations, which are metals, and anions are nonmetals. And they are held together by attractive forces. So they're mutually attracted to each other in a lattice, right? Alternating in all the different directions. So we can see that here we have cation, anion, and it would keep repeating over and over in 3 dimensions. And it's very strong. We also have covalent network solids. And these are held together by, a network similar to a lattice of covalent bonds. They tend to be very strong, very hard materials like diamond, silicon, and the silicon dioxide like glass or quartz. So they are really hard compared to molecular solids, which are discrete molecules. And these are held together by weaker forces. These are the IMFs. So both the covalent and molecular solids might have similar, right, nonmetals in them, but you'll see actually with covalent network solids a lot more metalloids that are in there. And our molecular solids, we'll look at their properties to help differentiate between them. All right, so two other types of solids we'll touch on at the very end are polymers. Polymers are long chains of atoms that are connected by covalent bonds. They start out as individual units and then they react to form these long chains, so like plastics. And they can be connected covalently like that, but then they can also fold on each other and be held together by, connect the chains by IMFs. And then lastly, nanomaterials. These are types of crystalline compounds that the crystals are really small, like 1 to 100 nanometers. And when you get that small, the properties of them are a lot different than when we're talking about the macro level. So there are a couple ways we can also organize solids. Firstly, being about their organization. So amorphous solids basically are ones that they have no order. So they're characterized by a distinct lack of order in their arrangements. So we can see obsidian here. There's no it bends that way, and then there's a deviation, and we can see a lot more a bending or kind of glassy look. And it does have properties of glass. Solids that have a regular repeating pattern, these are called crystalline. So the difference is amorphous, having no structure, and crystalline being ordered and structured. And so these are defined by the size and shape of the unit cell and the locations of the atoms within a unit cell. So you might be wondering, what is a unit cell? A unit cell, we would draw a cube. And basically what it is the smallest repeating unit that if we stack it in 3 dimensions, can produce the entire crystal structure. So that might look like having one atom in the very center and 4 atoms on each vertex that are holding them in. We'll look at some other ones in here. You do not need to really know a lot about what the unit cell is, but I do want you to know that a crystal lattice is made up of lots and lots of unit cells, and we'll look at that on the next slide. So here are some examples of unit cells. We have here's a cubic lattice where we have each of the corners of this lattice have atoms on them, and then this would repeat in all dimensions. We have body-centered where we have all of the corners have an atom on it, and then we also have one in the middle. We also have face-centered where again you have atoms on each corner, and then you have atoms on each face of that cube. And so it depends on the size of the atom and how they interact with each other, but we're basically going to get the most packed in structure that we can, because nature does not like empty space. We're going to try to pack them in as close as possible, and that's going to maximize attractions, and it's going to minimize repulsions. So it will just depend on what the materials are, what the different atoms are, and how big they are, and how they can all kind of fit together to really pack in as close as they can. Here we can see different ways that it can be organized by layer, and they can be stacked upon each other differently, but you do not need to really know a whole lot. The chapter goes way deep into this, but we're not going to cover all of that. And in here, it talks about this being metallic structure. So metals do conform to these cubic unit cells. When we get into ionic compounds, there can be other types of unit cells. But what I want you to know is that both metals and ionic compounds are going to have these unit cells and kind of pack like this. So building off of metals, we're going to talk about alloys. These are materials that contain more than one element and have characteristic properties of metals. So usually it is made up of 2 plus metals, but it doesn't have to be just metals. So we'll talk about that in just a second. And then this is a really nice way that humans have been able to change the properties of the metals in order to get it into a more optimum condition for like building purposes, or maybe like in the dentist's office when they're filling cavities, we want certain properties so it fills in your teeth and keeps it, also doesn't like wear out and oxidize and stuff. So alloys can be created in order to like benefit us. There are 3 different types of alloys, specifically talking about substitutional and interstitial. Starting with substitutional alloys, if we think about what the word substitute means, it means, right, to like take into place or take the place of. And so that's what happens. It's where another element will take the place of one of the metal atoms. Now, for this to happen, the atoms have to have similar sizes. So we would need to have 2 metals that have a similar size, similar radius. So that way it could easily be substituted. So gold and silver have similar radii to each other, and so they form a really good substitutional alloy in 14 karat gold. With interstitial alloys, these are ones, interstitial means between the space. And so this is where a second element fills the space in the lattice. So we have our metal lattice, and then we have tinier atoms that can fit in between. So for this, one metal needs to be way smaller. Or it doesn't even have to be a metal, but the other atom needs to be smaller, so it can fit in the little holes. And that actually helps to strengthen it. So steel is iron that has carbon built into it that makes it so the iron basically is fortified and strong and is not going to break as easily, it's not going to rust as easily. So yay for steel. And then heterogeneous alloys are kind of similar, where it's a combination. We might have the pure metal here being the dark part up here, and then the alloy being the, so here we have steel inside this one, and so we have the lighter color is the alloy, the interstitial alloy, and then we have the pure metal. So heterogeneous alloys are like where you might have the metal and then the alloy that's kind of not uniformly dispersed throughout. Here are some examples of some alloys that you might be familiar with. So Wood's metal is bismuth is the main metal, but it has lead, tin, and cadmium. It has a low melting point. It's used in sprinklers and fuse plugs. I'm going to go to some that we might be more familiar with. Bronze is copper alloy. It has tin inside of it, and it was more stable and used in early civilizations. Stainless steel is, like we saw earlier, well, it's steel, which is iron and carbon, but also has chromium and nickel, and that helps to prevent corrosion. It's used in cooking and surgical instruments. We have plumber solder, which is lead, but it is it's lead but with tin, and that helps to lower the melting point, making it easier to melt and combine metal, like solder the joints between metal pieces. And it's used in jewelry. Sterling silver is primarily silver with some copper. That helps to brighten it, so it's used in like silverware. Dental amalgam is silver with tin, copper, and mercury. Problematic if you were to swallow it, but it's really easy to work with, and the dentist can fill in your cavities with it. There are so many different alloys, so these are just some of the common ones, and you can see that they take the primary metal and make it so it has a use that humans are able to kind of benefit from. So intermetallic compounds are kind of similar to alloys in the sense that it is a compound of 2 or more metals, but they're actually compounds. Alloys are more like mixtures, and this is not a mixture. This is has distinct stoichiometry, definite composition. So with alloys, you can kind of choose your ratio of the secondary or tertiary elements that you put in. With these intermetallic compounds, they are a definite composition. So we have stoichiometry in there. So here for this nickel aluminum intermetallic compound, there will always be 3 nickels for every 1 aluminum. Versus if I had an alloy of nickel with aluminum, I can kind of choose whatever ratio of nickel and aluminum, and I'd mix it into it. So it's ordered, and so it will have like a crystalline structure. They tend to be more brittle than substitutional alloys. So much more similar to a like a compound. Like think about like salt, where you can kind of crush it and it's brittle. Where the alloys are more metallic and they can they're harder, so it actually strengthens it. I have been asked where intermetallic compounds are used, and they're really not very common, but they are used in high temperature applications such as in aerospace and energy. They make power generation systems like gas turbines more efficient, so you might see them in electronics sometimes. They tend to have magnetic properties, so you might find them in magnetic materials, catalysis to help chemical processes happen at a lower, with lower energy. So, but they're not very common in like our everyday life. So let's talk about the metallic bond. Metallic bonding happens because we basically have our cations. We can think of it as like a group of cations, and that's the nuclei inside here that are suspended in a sea of electrons. And this is called the electron sea model, and it does explain the fact that these materials are electrically, so they have electrical and thermal conductivity. They are ductile and malleable. So ductile means that you can stretch them into a wire, and malleable means that you can like flatten them or mold them into different shapes. And so, right, like if I was to knock on this atom, I would be able to like kind of shift everybody, but they'd all kind of be intact, and because those electrons can move around. So yeah, electron sea model, we have these stuck nuclei, and then the electrons are able to kind of freely flow in a communal way. Ionic solids are held together by electrostatic attractions. Between our cations and our anions. They have a very high melting point and boiling points, and they are what we think of as crystals. So whether you're thinking of table salt, which is sodium chloride, or baking soda, sodium bicarbonate, or even like calcium carbonate, which is chalk, or ammonium nitrate, which is fertilizer, or a component of fertilizer, they're going to be hard to boil, right? If I just put a bunch of salt on my stove and heated it up really high, it would never melt. That temperature is not high enough to get it to melt. In this case, the charge is actually centered on both the anions and the cations, right? So it's not my nuclei where my electrons can just float around. I actually have a charge, a negative charge here. This is an atom with a negative charge, an atom with a positive charge. And so they are, this allows it to be an electronic insulator, because you can't get that negative charge to move. If you move that negative charge, then it wouldn't be an ion anymore. You'd be giving a negative charge to a cation, and it would neutralize it. So that's not going to work. Now these tend to be brittle. So let's look at why. So if we look here at our like a single layer of a lattice structure, we have repeating cation, anion, and in all directions. And so we have really maximized the attractions here. If I was to apply a force, so they're applying a force to these 2 atoms to the left and these 2 atoms to the right, basically what you're going to do is you're going to shift your atoms, so that way you have these anions touching and these cations touching and anions, and like charges repel each other. And so this causes, when we stress these atoms and we shift them over so they're not attracted anymore to their neighbor, they're repulsed by their neighbor, it causes them to separate. And this is why these types of materials are very brittle, right? Like chalk, you apply a little bit of a stress on some chalk and that baby will snap. So it has to do with those charges of the ions, and are they repelling or attracting. So if you try to move them, they're going to now repel. So these also have a unit cell. These structures are going to have, the best structures are going to have cation-anion distance as close as possible, but the anion-anion and cation-cation distances are as far apart as possible. So our repelling is minimized. Minimize repelling. And we're maximizing our attraction. The last thing we're going to talk about is our molecules that are held together that have some kind of covalent bond. So both of these are formed with usually nonmetals. So if we start first talking about molecular solids, these are atoms or molecules that are held together by weaker forces, right? The LDFs, dipole-dipole, or hydrogen bonding. So they're individual molecules, right? So this guy is a molecule of benzene. And if I were to get it to a solid, right, cool it off enough, it's just going to be a bunch of benzenes that are stacked together and held together by dispersion forces in this case. So for molecular solids, their shape matters, right? That has to do with their LDFs as well as their their polarity and that kind of thing. Graphite is an example of a molecular solid because we have a single molecule of these carbon atoms that are stacked onto each other and stacked onto another layer of this molecule of graphene. Water is an example. All of the things we talked about in chapter 11 and even 10 with gases, any molecule we've dealt with, if we get it cold enough, it's going to, the intermolecular forces are able to hold them together. Covalent network solids, on the other hand, are atoms that are covalently bonded over a large network distance, and we have this regular pattern. They tend to have a very high melting point and boiling point. Diamond is an example of this. So diamond versus graphite. Diamond is these sp3 hybridized carbon atoms all connected in 3 dimensions, right, in this network to other carbon atoms. It doesn't have to be just a single type of atom, though. We have the same thing happen with silicon, with oxygen. We have 4 oxygens all held together by another silicon, and so on. And so it's just like this huge repeating structure here. And we would differentiate the network covalent solids but from the molecular solids based off their boiling points, melting points. Covalent network solids are really, really strong, and molecular solids aren't. They're a lot more, they tend to liquefy and boil a lot easier. I do want to make a note that even though when we do have more than one type of element, like silicon dioxide, it is in this really big structure, right, in this big network. But when I write it, I'm just going to write SO2. So that looks a lot similar to CO2, right? So it's like, how do I differentiate? Well, I think about carbon dioxide. It's a gas at room temperature. Silicon dioxide, that's quartz or glass, that's a solid at room temperature. Not all molecular solids are going to be gases, right? There are some that are solids at room temperature, but we think about like what's the melting point of silicon dioxide versus the melting point of carbon dioxide. And so we can compare the strength by those melting and boiling points. Some interesting stuff now. We're going to talk about nanomaterials. These are particles that are 1 to 100 nanometers in size in 3 dimensions, and there's been a lot of study about them. They're used in semiconductors. Because they're so small, they have discrete orbitals rather than having this like combo of all of the different atoms in there. Now this type of small material happens when we get to about 1 to 10 nanometers, which is where we're at about 10 to 100 atoms. So a really, really small amount of material. Quantum dots are an example of this, and these are usually metals that are used as semiconductors. So you can see that these are right here. We have cadmium, selenium quantum dots, and they're all the same material. The only difference between each of these samples here is how big the atomic radius is, or the diameter. So if I have 2 nanometers, I'm more of a blue. If I go up to 7, I'm more of a red. So that's pretty interesting that you have the same material and it can have different properties depending on its size. Metals also can get really, really small and become nanomaterials. If we look over here at this solution, this is actually gold, and it is how a lot of cathedrals and glass staining had been done in the past, is with nano gold, which I'm like, how did they know how to do this all the way back when these glass staining was being done? It's pretty interesting. I'm sure there's some good history in there. And then lastly, we're going to talk about carbon. So carbon, there's many, many, many different forms of carbon. You might think of carbon as your diamond or as lead on your pencil, and those are both examples of carbon. They are allotropes of each other, meaning they're the same material, but they just have a different structure. And until the mid-80s, we only knew that carbon could be diamond and graphite. But then what happened was there was a scientist named Buckminster Fuller, and he was able to form these discrete C60 molecules, which looks like these balls here. Since they look like a soccer ball, they were called Buckminster Fullerene or buckyballs, and they have been used, so they're really, really tiny because it's just 60 carbon atoms, and they have been used for drug delivery, energy storage, as well as strengthening materials. Now, if we take our buckyballs and we open them up, we can flatten them out. And so that is what a graphene sheet is a fully laid out carbon where we have these sp2 hybridized carbon atoms. And we know that if we have sp2 hybridization happening, then we have a p orbital here that is going to cause some double bonding between the nearby atoms. This causes this to be very, very strong material, and they are also very, very good conductors of electricity, which is awesome because not only are they strong, they're very thin, they're flexible, they're able to be used in electronics all the time. They're also used for strengthening as well. If we took our graphene sheet and we folded it into a cylinder, we get these carbon nanotubes. And these also are great semiconductors because we still have that pi bond in there. And they can allow for some metallic properties and semiconducting properties without doping it with other like heavy metals. And if you've ever had or seen anybody who has a carbon nano fiber bike, then these are very lightweight, they're very strong, and they're made out of carbon nanotubes. There's so much more information about materials like polymers we didn't even get to go into. This is such a rich topic right now, and a lot of research is being done on it. So if you're interested, there's a lot more you could read about in the textbook.